Welcome to Action-Reaction Forces, the podcast where we explore Newton's third law through real laboratory investigations. I'm Amara, and today we're diving deep into one of physics' most fundamental principles. For every action, there is an equal and opposite reaction.
I'm Marcus, and we're excited to break down what this actually means in physical interactions. You see, Newton's third law isn't just a theoretical concept, it's happening all around us, and we can measure it precisely in the laboratory.
Exactly. Today, we're examining two classic experiments, tug-of-war and collision dynamics. Both reveal something fascinating about how forces work in pairs. Let's start with tug-of-war, which might seem simple, but contains profound physics.
In our laboratory investigation, we used two force sensors connected to participants pulling on opposite ends of a rope. The question we asked was, are the forces truly equal and opposite? Our data showed something remarkable.
When neither person was winning, meaning they were in equilibrium, we measured force magnitudes of 12.9 newtons in one direction and negative 12.8 newtons in the opposite direction. That's nearly perfect equality. The difference was only 0.1 newtons, well within experimental error.
But here's where it gets interesting. When one person started winning, the magnitudes decreased. Person A, pulling with 10.3 newtons, received a reaction force of negative 10.1 newtons from person B. The forces remained equal and opposite, but the overall magnitude changed.
This teaches us something crucial. Newton's third law doesn't determine who wins the tug-of-war. The action-reaction pair is always equal and opposite, regardless of the outcome. What determines the winner is the net force on each person, which depends on their mass and the friction between their feet and the ground.
We also tested what happens when the participants have different masses. When person B had significantly more mass than person A, we measured forces of 43.3 newtons and negative 44.1 newtons. Again, nearly equal and opposite, but the magnitudes increased substantially.
The key insight here is that the action-reaction pair magnitude depends on the interaction itself, not on the masses involved. A heavier person can exert more force, but that doesn't violate Newton's third law. It simply means the interaction involves larger forces overall.
Now let's shift to our collision experiments. We used two carts equipped with force sensors, allowing us to measure the forces during impact. This is where Newton's third law becomes even more dramatic.
In a collision, two objects exert forces on each other for an extremely brief time interval. Our force sensors captured these impulses with remarkable precision. The data consistently showed that the force exerted by cart A on cart B was equal in magnitude and opposite in direction to the force exerted by cart B on cart A.
This is true regardless of whether the carts have equal masses or different masses. A light cart colliding with a heavy cart experiences the same magnitude force as the heavy cart experiences from the light cart. The difference is in the acceleration each cart undergoes.
Using Newton's second law, F equals ma, we can understand why. If both carts experience equal and opposite forces, but one has greater mass, it will accelerate less. The action-reaction pair is always equal, but the consequences, the accelerations, depend on mass.
This distinction is absolutely critical for university-level understanding. Students often confuse the forces with the accelerations. Newton's third law guarantees equal and opposite forces. Newton's second law determines what happens as a result of those forces.
Let's consider a practical example. When you jump, you push down on Earth with a force, and Earth pushes up on you with an equal and opposite force. You accelerate upward dramatically because you have small mass. Earth barely accelerates because it has enormous mass. The forces are equal. The accelerations are vastly different.
Our laboratory data from both tug-of-war and collision experiments validates this principle quantitatively. The force sensors provided measurements accurate to within tenths of a newton, and in every case, the action-reaction pairs were equal and opposite within experimental uncertainty.
What's particularly elegant is that Newton's third law holds regardless of whether objects are in contact, accelerating, or at rest. It's a universal principle that governs all interactions in classical mechanics.
The implications extend far beyond the laboratory. Understanding action-reaction pairs helps us design safer vehicles, predict orbital mechanics, and comprehend everything from rocket propulsion to biological locomotion.
As you continue your physics studies, remember that Newton's third law isn't just about equal and opposite forces. It's about recognizing that forces always come in pairs. No object can exert a force without experiencing an equal and opposite reaction.
Our experimental investigations have shown us that this principle manifests consistently across different scenarios: static equilibrium in tug-of-war, dynamic interactions in collisions, and everything in between. The mathematics is elegant, and the physics is profound.
Thank you for joining us on Action-Reaction Forces. We hope this exploration of Newton's third law through laboratory data has deepened your understanding of how forces work in our universe.
Keep questioning, keep experimenting, and remember, every action truly does have an equal and opposite reaction. This is Marcus, signing off.
And I'm Amara. Thanks for listening.